almost clear. There's nothing much as such.
Okay. So are
Uh,
you guys practicing? Have you practiced? Have you used any different uh, data sets and tried all the algorithms on your own? So I just want to check, like, if you guys are comfortably, you are able to train the models, or you're facing any challenge anywhere. So fine. In the end, as I mentioned, I will wrap up. Okay, I will revise all the algorithms again, and I will give you a complete picture. Like whenever you will get any new use case, how step by step you have to tackle that particular problem. Okay, and in that whole process, I would like that whole session to be more interactive. So I would expect you guys, to tell me like what should be the next task, and in that way, it would be helpful for all of us, like um, to evaluate ourselves also where we stand, and whether we have a complete clarity. And if anywhere there is any gap in your understanding, I will try to address that, and in that way you will able to understand overall end-to-end process for uh, solving any machine learning problem. Okay, so but today let's go with this convolutional neural networks. Okay, so we discussed about neural networks, artificial neural networks in the last class, and there we discussed about a single layer neural networks, multiple layered neural networks. So the single layered neural network, where we will just use one hidden node, which we called as a single perceptron neural network. And these hidden nodes are also called as perceptrons. Okay, I don't know if I covered that point. So somewhere these neural networks will be called as perceptron network. Okay. So perceptron is a hidden node where the whole processing and the transformation of the data happens. So if any neural network, if there is in the hidden layer is if there is only one single perceptron, that will be not called as a deep learning algorithm. But if the hidden layers um, increases and the hidden nodes also increases, and hidden nodes means perceptrons, if we have multiple perceptrons in the network, then it will move to a deep learning family. So the artificial neural network with multiple layers and multiple perceptrons are called as deep learning models. And we have seen that how you can add more hidden layers, how you can add hidden nodes, and how you can configure those hidden nodes uh, by choosing the right configurations, like activation functions, or even the gradient descent uh, techniques. So, but that is more of a vanilla or simple neural networks where you can pass the structured data. So if you have in the data set, if the data is columnar, means column based, proper rows and columns are defined, then you can pass that kind of data to these kind of neural networks. So that is known as KNN, okay, artificial neural networks. And we have seen that there are certain frameworks like Keras, TensorFlow, and then PyTorch. These are all deep learning frameworks where you can construct complex neural networks also, be it like multiple layered neural networks, or you can also build other different kinds of neural networks which can even process unstructured data. So one such neural network is convolutional neural networks, and this convolutional neural networks is primarily meant for image processing. So we call as a computer vision algorithm. So now, when we are talking about artificial intelligence, so you need to understand what is this artificial intelligence? See, artificial intelligence is also sometimes called as cognitive analytics. See, we have cognitive skills, right? In humans, we have cognitive skills. We can, so these five sense organs, okay, we use, and those are known as cognitive, basically senses, like vision, speech, hearing, touch. Okay, so these are all our cognitive senses, based on which we as humans, we are considered as intelligent creatures. Okay, because we can think, we can comprehend, we can speak, we can express our feelings. All that thing is possible. So now this artificial intelligence means we are creating a machine which can also able to do all these things. So now when we have to train these machines, so these kind of skills we need to embed or integrate into the machine. So the most important one skill is vision. So vision, so now we are saying computer vision. So here computer or the machines, they will get that vision capability through which they can process the images, they can process the videos, they can do the insights, and you can take some, and you can also make certain actions or certain decisions. You can also do based on all that insights. So this whole thing basically is used for automation purpose primarily, okay, or else product development. So when you see your mobile phone, so the cameras when you on, or any other applications you might have seen, right? Kids basically use those kind of apps where it put some headgear on top of your head, and all those things, crazy things, okay, can be done through that app. So those are all based on computer vision. So what these machines can do is it will go and understand that image. So if it is a face, then it understands it's a face. And in that face, it will also detect the landmarks. What is landmarks? Where is the eye? Where is the nose? Where is the mouth? And once it identifies that particular landmark, you can overlay some kind of object on top of it. So now if it has detected the eyes, you can put some eyeglasses or some kind of shades on top of the eyes, and you can have that kind of modified image. So now the same concept now people are using in a much more creative way. So now currently we have developed one solution for one of the retail customer, where the people can try garments and clothes virtually. Okay, so you just take your image and you can select some, like for example, a jacket or a shirt or anything. Okay, any other apparel, and you just say try. So on your image, it will go and overlay those kind of clothes. So in that way, instead of going to a retail outlet and going and trying the clothes virtually, also things can be done. So these kind of, and now this is evolving, this computer vision, and we have used GPT vision models there, which is much more, I would say, sophisticated, and those are state of the art techniques, to process the image. But the fundamental algorithm starts with CNN. Okay, so any subject, if you are s- studying, then you have to start from the basics. Okay, so now first problem is, if we get images, first of all, how to read those images, right? It is basically unstructured data. And all these algorithms, by now, you might have seen that all these are mathematical based, right? The way the gradient descent is working, those are all partial derivative based algorithms, right? So automatically, these kind of algorithm cannot understand the unstructured data. You have to do some kind of processing and convert that unstructured data into a structured data. Now, first of all, you need to understand which all data you will call it as an unstructured. So we have discussed, right? Unstructured means a data which you cannot view in the form of tables. That is known as unstructured data. It could be text, it could be logs, it could be images, it could be video, audio, whatever it is. Okay. You cannot view the image or the video frame in Excel or in any other table format, right? So now what to do? Now we need to understand, first of all, if you get any kind of an unstructured data, you need to think about how to convert this unstructured data into a structured data. When it comes to images, we talk about pixel values. And the good part is, like, whatever unstructured data, digital data you deal with, it can be converted into a structured data in some or the other form. Okay. So now in this images, these are all pixel values. So we talk about HD videos, we talk about HD images, high dimensional images. What do you mean by high dimension? So there it's all about the pixel values. So if your image is, sorry, if your image is 5 by 5, so that means you have 5 columns and 5 rows. Okay, something like this. And here in every cell there will be some pixel values, and this pixel values will range from 0 to 255. Okay, so I will show you. So this is basically if I want to change this color. So if you am going here, I'll go here. So in any of the applications, if you go to more colors. Okay, so these are RGB colors. So basically, these are nothing but the pixel values. Okay, so it can take maximum. Okay, max. If you put it as 0, 0, 0, so it will become black. The maximum would be 255. So 0 to 255 means 256 values. Okay, to white. So the whole gradient uh, will range between black and white. Okay, so black means all these three colors will, the pixel values would be 000. If it is 255, 255, 255, then it will, the color would be white. And the good part with this vision is any color if you want to find out, it will be a mix of these three colors, RGB, red, green, and blue. Okay, and the same logic goes with videos also. Okay, so in the televisions and all those things, these are also a combination of red, green, and blue. So in the older days, there would used to be a picture tube, right? In that picture tube, I don't know whether you have experienced or not. There would be a mix of these three colors, RGB, right? Red, green, and blue. If any color doesn't work in that picture tube, so you will get that shade. So you might have experienced that sometimes a screen looks complete blue. Okay, so it would be too much of bluish on that. Sometimes too much of reddish. So that's the problem. You may face if any particular channel doesn't work. Okay, color channel doesn't work properly. So that was the whole intuition behind, and people thought that if we can able to extract these pixel values and that too at these three different color channels, so that could help us in terms of analyzing the images. And that was the whole concept people have considered. And now, whatever kind of image processing you do, you will see that these unstructured data will be converted into the pixel values, and it could be either on the grayscale. If it is a grayscale, then you will not get three dimensions as red, green, and blue. And I will also explain where you have to go with the three channel, where you have to go with only on the grayscale. Okay, but you can convert these images into a proper numerical data, structured data. Okay, so now how does CNN work? So the full form is convolutional neural network. So convolutional means basically it kind of mix all the information together. Okay, so information coming on from the red channel, from the green channel, from the blue channel, and it kind of mix it, and then it will bring out the insights. So for example, when you look at the images, sometimes colors will give you a lot of information. So if you want to distinguish between cat and tiger by face or by structure of that of the body, if it is a grayscale, you may not able to distinguish what is tiger and what is cat, right? But if you add color to it, you can easily identify. So we need to understand where the color is also important. If the color is important, then we have to go with all these three channels. If the color is not important, only the shape and size is important, then you can convert that color image into a grayscale, where the entire image would be in a black and white gray shade, and then you can process it. So this convolutional neural networks will have some initial layers which will be completely for image processing. And once the image is processed and the data is converted into a structured data, then it will be passed to this ANN. So now this is ANN, which we have traditional neural networks, which we have discussed, or also called as fully connected layer. Okay. Now, before this fully connected layer in CNN, you will find different other layers, which is primarily meant for image processing. Okay, because you cannot directly pass the images to ANN, to process, because the ANN requires a structured data. Now, this whole layers before ANN, helps this particular algorithm to pre-process and to extract the data from these images in the form of tabular format or in the form of tables or in a structured format. Okay, so now these are inputs. Okay, let's suppose this is a car image. I'm passing it. Now here, first layer would be a convolutional layer. So this is very, very important layer of the CNN. So what is this convolutional neural network does? And in this CNN, you notice that in convolutional layer, by default, we always go with ReLU. You can use other activation functions also, but primarily the most suitable activation function is ReLU. So what this convolutional layer does is it extract the features. It extract different kinds of features. So there would be some convolutional or we call it as feature maps. What this feature map does is it will extract some key features, okay, from the images. So for example, now if let's suppose this is a face, so this feature maps, for example, one feature maps, it will go and try to find out if there is any kind of a circular pattern in that particular image. If there is any another feature map, go and extract if there is any kind of a vertical kind of a structure there in the image, or any other, or one of the feature probably may detect some edges in the images. So like that, we have multiple features. And the good part is you need not to worry about how many feature maps you need to apply or use to extract the features. Automatically, this CNN, picks up certain feature maps and it will try to extract the important features. So here, if you have to classify, so the CNN basically is a very good algorithm which can classify the images. And here the use cases could be enormous. Okay, could be several. For example, you want to have some surveillance, okay, based on the computer vision. In the CCTV cameras, you can embed a model which can detect or which can classify a person, okay, in that a restricted zone. If anybody is a person enters into that particular restricted zone, it will pass the alert. So here we may have to train a model which can classify the humans, whether it's a human or not. Okay, or else you can go even specific, even more uh, specific use case where you can classify certain authorized humans only who are supposed to enter into a particular zone. There are multiple other techniques also. You can even create some kind of boundary of a zone, okay, with the help of coordinates. So because the CCTV camera would be fixed, right, and you will get a fixed frames, okay, every time. So in that particular image, you can find kind of set the coordinates. So you can take this coordinate, this coordinate, this coordinate, this coordinate, and you can draw the boundary. If anything enters inside this boundary, it will detect and it will pass the alert. That is one. Second is like one more use case I would like to talk about is it's a manufacturing plant and they wanted this image classification model to run on the cameras which are mounted on the entrance of that particular plant, entrance gate of that particular plant. And in this particular plant, there are different kinds of vehicles which passes. Okay, it could be a small vans or it could be a big trucks. So they want to classify how many vans entered, how many medium trucks were entered into the plant, and how many big vehicles entered into the plant. So it's not about just classifying the vehicles, detecting the vehicles, but also classifying the vehicle. So now this is at the entry gate. So here it will count like, okay, the lightweight vehicle 4 passed into the plant. Okay, the medium was 3, and then heavy were 2. Okay, this is at the in gate. Now that the exit gate, again, whether how many light vehicles have moved out of the plant. So 3. So there is a one vehicle still inside the plant, and they are also measuring the time. So if it is exceed a certain time, now they want to take an action, or they want to go and check like why it is taking so much of time for unloading or for coming out of the plant. So this kind of monitoring they wanted to have, at the plant level. So for that, we have built a solution. So like that, you have multiple use cases, but you need to understand the underneath the technology and the framework. It will remain the same. It's just like you have to train the model or customize your model based on that specific data or specific scenario. Again, recently now we are talking to one of the museums, okay, in Middle East. Now they want to count unique visitors who are coming to the museum. Okay, so here detecting humans, then classifying the humans, and then running the counter on top of it. So for example, if I'm there, I've been detected by the camera, so it will put a count as 1. So now I went somewhere else, and again I came to that particular spot. Again it will detect, again it will classify. It will also go and check whether I was counted before or not. If I was counted, then it will not count. If I've been found as a new visitor, then it will go and increase the count. So this is some kind of solution they are expecting. So we are building a POC for them. So let's see, if everything goes well, then we have to go and deploy these models in their environment. And in the computer vision, again, one thing you may encounter is these are heavy models because you are using images. And now if you are using high dimensional images, so it's a huge amount of data which you have to process. So and in the computer vision, like surveillance, right? It should not take a lot of time. If something entered into a restricted zone, and if it is taking around 15 to 20 minutes to process and then raising the alarm, so it's of no use, right? It has to be real time. As soon as somebody is found in the restricted zone, immediately that action has to be taken. So here comes, I don't know whether you have heard about edge devices. So here, people rather, instead of extracting the data or reading the data from these CCTV cameras and then processing it in the cloud, and then after processing again, passing that output to some other application. So it definitely there would be some latency. Now, some of the customers, what they want is they want these models to be embedded inside the device itself. So for that, it does not require any internet. And if there is any problem with the connections, internet connections, again, it's a problem. So if there is a high risk kind of a scenario, then usually people would like to embed that model inside the device only. So that we call as an edge device. So edge means in the device itself, there would be you can call it as a processor, a small processor, and there would be small memory also inside that. So you can run
It's
a small model. Yeah,
like in IoT devices, like we have an
IoT.
IoT device.
I, Yeah, you can call it as IoT devices, but IoT devices again will have multiple. Some of the IoT devices only generate data, it will not process it. For example, sensors. Like you might have used a smart watches or Fitbits kind of a thing, right? So these you can consider as a device where even the data is getting processed. So first of all, when you are running, when you are walking, when you are doing some activities, it is capturing that data, and then inside that it is processing, and then it is giving you some insights, right? Some facts. So instead of, and if there is no connectivity also, still your Fitbit will give you some analysis, though it will be not connected with your mobile phone, and your data would not move to your mobile phone. But on the Fitbit itself, you can able to look at the data. So somewhere where there could be internet connectivity issues, or they don't want any kind of latency in terms of uh, processing the data, there we go with an edge device. Here again, as you mentioned, IoT team also would be also considered for this whole deployment, because we as a data scientist, we have no idea about the hardware, right? So some nowadays even the customers are asking also, what kind of hardware would you propose or recommend where we can run these kind of models? Okay. Again, one more example I'll give you. It was more of a handloom kind of a scenario where uh, I'm forgetting the name. There's a spindle kind of a thing where the entire thread rotates. Okay. Now, what happens is when all these spindle or cylindrical structures, they move, they rotate, this thread goes and get accumulated on that particular spindle. But what happens sometimes? Sometimes this thread breaks up. Okay, and breaks up, and it creates a hole, and whole thread will get wrangled up there, and it is a big problem for them, to clear out that whole thing. So, so what they want to is, if they can detect any kind of a thread break, immediately we stop that spindle, so they can avoid those kind of scenario. So what is happening now when they are handling hundreds of such kind of machines, where on the real time these things are happening, and they want some kind of a vision based solution which can continuously monitor where the break is happening, and is not very thick kind of threads or ropes. Okay, these are very, what do you say, delicate threads, and in one single spindle there are like 10 to 20 different threads are getting rotated. So it is a high speed camera we need, and that kind of detailed images we need to have, and then only the processing and detecting those kind of breakage can be possible. So now there are multiple problems. One is like high speed processing we need, and the second thing is like even the training the model and detecting that the thread break is also a problem. So we tried, but they didn't have much many images, clear images. So we kind of said that, okay, once you share that data with us, then only we can able to proceed. So I don't know, where we are on that. So, but there the ask was, they were asking from everything. They are asking hardware. You tell us like what cameras. You are saying images are not good. Now tell us, recommend us what images you want, where you want us to mount those image cameras, and what angle you want the visions or the images. Okay, how many images you want, and the second thing on the latency, we want like within fraction of seconds, it should give us the results. So even deploying it on the edge was also their ask. So yeah, so if it would have come, then it would have been a good project, but due to insufficient data, we couldn't move forward. Yeah, so somewhere in computer vision, edge devices, you will hear a lot of times. Okay, so if you want to get more expertise in this particular area, then you have to get into all these things. And this computer vision is again a different, altogether a different ocean. It's a different space. So currently we are just understanding the overall picture, but again, if you want to understand every minute details of it, again, it's going to take a lot of time, and it's altogether separate subject. And when you go to colleges and all for MSc and for any kind of masters, there you will find this subject as a separate specialization. This is one, and the natural language processing is another such area. Okay, so yeah, so to coming back to this particular algorithm, we have images. Yeah, before covering that, okay. So guys, do you think videos and images, they are two different things? Or do you find any similarity between images and the videos? Or do you think that it needs to be analyzed separately, differently? What's your take?
I mean, images is like in one single moment of, 1 second you take a
Static.
snapshot.
Mhm.
While video will be like it's a continuous thing
Yeah. So
over a
basically,
period of time.
right. So basically, see, there is not, it's the only thing is like image is a static and the video is more of dynamic, and it keeps on changing. But consider the video as nothing but a set of images. Okay. So for example, you take couple of images and put that into some kind of a slideshow and make it automatic and change those images in every 1 second, then it will look like a video only. So when we are processing the videos, you might have seen that, okay, the videos in any application would look like this. Okay, here something happened, then something else happened, then something else has happened. Okay, and you can trim the video, you can take out certain part, and all those things are possible. So now while processing the video, what we do is we consider certain frame per second. So frame per second means, frame means every uh, static part of that video, right? So at this particular minute and second, whatever is seen in that video, that will become a frame. So frame by frame, if you analyze, and every frame you can consider it as an image, because again every frame is a static, right? So if you analyze frame by frame, then you can able to analyze the video, what is happening in this video. Now we have certain kind of generative models where you pass the entire video and it will summarize you the entire video. It will analyze, it will say that, okay, there was a person, who was riding a bike and then he met an accident, and he was taken to hospital. It will kind of describe the entire video. So video, there is no altogether a separate kind of algorithms. It will be also treated as an image, but the only thing is like initially you have to configure something where you have to decide what FPS, like frame per second, you have to process and how you want to process. And then it will, that many frames per second, it will go and pick up, and it will go and process and convert that data. And then you can either give it to CNN, right? So CNN, for example, if in the video surveillance, okay, if you want to detect the person, right? So in this particular frame, there is no person. So this frame will go and pass to the CNN, and there is no person, it will not detect any person. Now again, the second frame will pass. Now let's suppose in this particular frame, there is a person. Now again, now this is nothing but image. After image, we are passing to this algorithm to detect if there is any person or not. Okay, either you can do it uh, what do you say, offline, like you break the video into multiple frames and frame by frame you pass it, or else you can do it real time, where you just pass the video and you decide the frame per seconds, how many frames you have to consider per second, and that many frames will be passed to this model, and it will go and find out the person. Okay, so why I'm covering this is because again, in if somebody is interested on computer vision, they may ask you this question like during the interview, like how you will process the images or the videos. Are they two different things, and do we need to analyze altogether differently? There you have to say that no, it's almost a similar thing, and the video consists of frames, and the frames we can consider it as an image, and that's how we can use some traditional image processing technique on the videos as well to process and to derive some insights. Okay, so now let's suppose we have this particular image. So in this particular image, we have to go and extract certain features. So as I mentioned, there are certain feature maps which will convert this, which will extract certain important features from the images, and those are considered as a convolutional map. And now, as I mentioned, this data is going to be huge. Okay, so just imagine if I am taking high dimensional data with, till 255 pixels. So I will get, so it would be 255 columns and 255 rows. Okay, so now if and if I feed the data at this dimension, it's going to take a lot of time to extract the features, not about just processing, but extracting the features. And just imagine in a vision how much minute, features needs to be extracted. For example, if I want to classify the cars and the trucks, if you look at the structure, it is almost the same, like four tires, two headlights, boner, something a similar kind of structure. But if you want to train a model which can clearly distinguish between the car and the trucks, then you have to process lot of and you have to extract a lot of minute details. So that becomes challenging. So to reduce the size of the data, we use this pooling layer. And this pooling layer is just like PCA, okay, what we discussed. It converts the high dimensional data to a low dimensional data, but again, it will make sure that very little information is lost. So majority of the information, it will keep it intact, and whichever information is not relevant, kind of get can be removed. Okay, and now it's not just you can go with only one single convolutional pooling, you can add multiple layers. So now after this data is got compressed, you can again run some convolutional maps, okay, or feature maps on top of it. Again, you will can try to extract some more features out of it. Okay. So like that, you can add multiple and the data will get reduced. And then once the data, and these are all data is in the matrix format. Okay, I will show you, okay, how these matrix are constructed. And once this matrix has been constructed before passing this neural network, now this data will get flattened. So for example, now you have a matrix like this, 3, 4. Now this will get flattened. So flattened means it will be like this, 2, 1, 3, 4. One single, and this would be your input parameter 1, input parameter 2, and 3. Once the data is in this format, now we know that how we can plug that data to this ANN, traditional ANN network. And this we have discussed. You can add as many hidden layers you want, and then you can have an output layer where you can classify whether this particular image is a car, truck, van, or bicycle, whatever it is. Okay, now let's talk more about each of these layers. Now, as I mentioned, this is the image. If you are going with a colored image, then it would be a 3 color channels. And in every color channel, there would be a different number. So if you add this 4, 9, 35, you will get some different color. Okay. So for example, here the gradient of red would be high. So in this particular image, the red color gradient is very high on the top left corner. Okay, that is something you can, this model can understand by these numbers. For example, here, the number is less on red, but the number is high on green, but not that high. So, but it would be a little tinge of green color in this particular corner. So here, the shades of the color at different region of the image will give some information to this particular machine, okay, to understand. And now we are saying, okay, if there is a high red intensity at the top and green intensity below, and then we are also passing the output also to this to understand if this kind of pattern is there, then consider it as a particular object. Like that, we are passing multiple images. Then this algorithm will understand, okay, if the color patterns are something like this, so the image or the object should be this. So that's the reason it is called as supervised learning. Okay, so now if we are passing cats and dogs images, Okay, so it will understand if the color, the shape, and the size is something like this. It is mostly it is a dog. Otherwise, it is a cat. Okay, so something like that can be understood by this algorithm by these numbers. So these numbers are important. Okay, and in computer vision, we have a very standard library known as OpenCV. CV means computer vision and is an open source package in Python, OpenCV. In this, you go to the website. This has you will find a separate website for this. Okay, if you go to the documentation, they will give you several techniques of image processing. This is primarily for image processing. So in this, by using this particular package, you can rescale it, you can extract or convert that into a grayscale, you can compress the data, resize it. Okay, you can do a lot of things. Okay, there is a one single uh, function which through that function you can do whatever things you want. As we have used pandas, so basically it is like pandas for images. So you can do a lot of transformations, data analysis, and all those things through this OpenCV package. Okay, so here we have 4 rows, 4 pixels, and 4 columns. Okay, so there is no headers. Now we have this filter maps. Now we have that input data like this. Okay, which so we have an image here, and that image will converted that into this particular pixel format. Okay, which is more of a structured format. Now these are the filter maps. These are filter maps are nothing but these are a 3 by 3 matrix. Okay, which you can consider it as a scanner. Okay, for example, for S detection, these are the feature maps which you can use and apply it on these on the images, and it will go and identify where all the edges are there. Okay, you can even transform the data through this filter maps. You just apply that, and it will make the image more sharpen. Okay, it will blur the image. It will identify certain patterns. A lot of such filter maps are available. In convolution neural networks, the algorithm which we will use, it automatically picks up certain filter maps which will enhance the quality of the image, and at the same time it will go and extract some important features also from the images. Now, how does that work? How it works? These filter maps, as I mentioned, it is 3 by 3 matrix. Now, if you see this orange color one, this is a 3 by 3. So in that there is a small red number, right? 101011, right? So these are, and if you have noticed, these are not big. These are mostly the binary values, 011. Now this is all mathematicians. They have, and this mathematics is magical. So just based on these 3 by 3 matrix with binary values, you can identify certain important features out of the data, out of the image. Now see, now this acts as a scanner. Like you have an image, and this is scanning the entire image from top left to bottom right. Okay, and how you want to stride this particular filter map, and again for that also you have an option. Okay, here it is striding 1 by 1, but you can stride 2 by 2, so it will shift 2 columns as it moves. Okay, and 2 rows below. But here we are using one stride, so it is shifting 1 by 1. Okay, so if you have a big images, you can go with a higher stride. If you have a smaller images, go with a lower stride. And then even you can do some kind of a padding. So for example, there is a very important feature is kind of available at the top left corner. So as it starts from here, probably this particular information may miss out. So what we can do is we can add some padding around it. So for example, some blank rows on top of this, or some blank cells around it can be added. Okay. So if you say padding of 1, then it will add one column and one row, okay, around this particular data. So for example, it will get added like this, some padding, okay. And now your whole scanning will start from this particular corner. So in that way, this information will not will not get lost, okay, and it will be retrieved completely. Now, how this calculation is happening? It is a simple calculation. So now you have, so let me stop it here like this. Okay. And so here the red colors, these are like filter maps. Okay. It is a matrix of 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. Now this data, the green data, okay, it is now you are seeing that it is having only 0 or 1. So if it is a grayscale, then you will get something like data is 0 and 1, okay, where 0 means black, 1 means white, or 1 means black, or 0 means white, okay, if it's a grayscale. Now this feature map will get applied on this particular data. Okay, and I will also show you how on RGB channels it work. But let's suppose this is a gray where we have only one matrix of the image. Wherever there is a darker shade, now it is marked as 1, otherwise it is marked as 0. Now this filter map will be applied on this. So it will now, this filter map is at this particular section of this particular matrix. Now this 1 into 1, 0 into 0, 0 into 1, 1 into 0, like that the multiplication will be done with this feature map. And after that, it will sum all the values. Now that value is nothing but this 4.
Sir, we are able to
Yep.
see the PPT.
Sorry. What you are able to see?
PPT only.
In PPT only I'm explaining this.
Okay. I thought you are writing something. Okay.
No, I'm writing also same time on the PPT. Are you guys able to see it? I've drawn a matrix here.
Yes.
Yes? Okay. So now this is the feature map, okay, 3 by 3 matrix. Now this 3 by 3 matrix, if you see here in this part section, so this is your feature map. This feature map is kind of moving and scanning the entire image. And when it is scanning, it is picking up that again 3 by 3 part of the image, and then this multiplication is happening, and based on that, the values are getting generated. Okay. Now this is known as convoluted features. Now what you have done is now here it is a grayscale only, but here in the grayscale also the black and the white colors, with these two colors, we are finding out certain features. Okay, so here, this whole data, which was like 5 by 5. So after this applying of feature map, this has been converted into 3 by 3. There's some reduction in the size of the data. Now it can be further reduced by passing it to the pooling layer. Now here I just explained one feature map, but like that there would be tens and hundreds of feature maps based on the data. Okay, these algorithm can extend and can use, and it will try to extract that many features. Okay, now this is about RGB. Now, as I mentioned, if it is a colored image, then you have to, then this machine, this algorithm has to analyze the data on all these three colors. And at the same time, it cannot analyze independently, because any color is a combination of red, green, and blue. So you have to see that in the image at particular area, what is the color gradient, whether it is too much of reddish or greenish or bluish. Okay, that it can happen only if all these channels are getting processed parallelly. Okay. So now, let's suppose this is one of the feature maps. In some of the books, it is also called as kernel. So you know about kernel, like in support vector machines we have discussed. It is some transformation is happening on the data through those kernels. So here with the feature maps, we are going and extracting or transforming the data to some other form. So that's the reason it is also in some of the books called as kernel channels. So this is my red, and here's some kind of padding I have done, okay, on top of every channel. And again, it is there is no thumb rule for this. If you if you are adding some kind of padding in the image, it will take more time. Okay, if you don't add it, certain information could be lost. So you have to take a trade-off. So first go without padding and see that whether how much accuracy you are getting. If the accuracy is not good, then you have to go and add some padding. You have to first go and look out certain images, why the accuracy is not coming good for certain images. If you see that the features, the important features are located at the corners, then you can go ahead and add padding to it. So here the multiplications are happening based on these feature maps, and it is generating certain numbers. Okay. Now, as I mentioned, when it is red, green, and blue, independently, we cannot go and store that numbers. We have to combine all the numbers which are coming out of all these three channels and then store that number into one single file, single matrix. So from the red channel, this is the number coming. From the green, this is coming. From the blue, this is coming. And then they are adding certain bias term also, like, and this gets added automatically. Okay. And now the numbers are getting updated here. So here, where we have seen only one single channel, which is more of a black and white kind of an image, there you will get only one single output. But here in the red green, we are getting three different outputs at three different channels. And then we are combining all that output to generate this particular single output. Okay. Now comes the pooling. Now what the pooling does is, again, you decide like what kind of pooling you want to do, 3x3 or 4x4. And every time feature maps or even in the pooling, you have to consider the square matrix. The rows and columns should be same. So here, again, I will just pause it. Okay. Now look at this. Okay. Now it is an empty frame, okay, which is getting scanned on this particular matrix. Okay, here there is no multiplication we are doing. So firstly, it will take 3x3, 3 column and 3 rows, this particular block. And in this particular block, it will either we can go with max pooling or an average pooling. Generally, we go with the max pooling because it is easy to process. So what it does is, in this particular frame, it finds the maximum number. What is the maximum number? It is 3. So it will go and capture that value 3. Now it will stride 1 towards left. Now this would be the part now. In this particular part, it will again find out the maximum number. Now that is 3. Either we can go with a max pooling where it will picks up the maximum number, or else we can go with an average pooling where it will take the average of all these three numbers, all these 3x3 numbers. Okay. So for example, now this is my matrix. If I apply the max pooling, so in this particular part, what is the maximum number? It is 20. Now I'm going with a stride of 2. So after this particular frame, the next frame would be this frame because it's strided by 2 columns. Now this would be the frame. And if I'm applying 2x2 pooling. So in this particular frame, what is the maximum number? 30. It will go and capture 30. Now it will stride down. Again, 2 positions down. Now this would be the frame. Here the maximum number is 37. It will picks up 37. Now here it will again stride and it will picks up the maximum number 112. Now similarly for the average pooling, it takes the average of these 4 numbers. Now that would be 13. Again, average of 4 numbers, that is 8, something like that. Okay, it will identify the average. Now if you have seen that it is earlier it was 4x4 matrix. Now after the pooling, now it has become 2x2 matrix. So pooling layer is primarily meant to reduce the dimension of the data. And why we are going, you might be thinking that, okay, we are going with max pooling, probably we may lose the data. Yes, we may lose the data, but it will make sure that whatever the important feature existing in that particular section of the image, that is at least get captured. So that's the reason it is going with max. Max will focus more on the important feature. Where is how much, what is the important feature existing in that particular section? It will picks only that. While average, what it does is it will overall, it will try to pick the information, but in a more compressed way. Okay. So depending on, whatever suits your data the best, you can go with either maximum pooling or the average pooling. So I'll take a pause here till this point. Anybody has any question? Because these two layers are the most important layers of convolutional neural network, and these are the two layers which makes this particular algorithm useful for image processing. So you understood this convolution layer, guys? Is any question on this particular topic? Okay, it's clear. Then we'll move ahead. Now this is for colored images. And now once we have got this output coming out from the convolution layer, then we can apply this pooling layer. So pooling layer, in the pooling layer, we can consider any small square matrix, and that acts as a kind of a empty frame. And in that particular square matrix, it will go and either picks up the maximum value or it will go and calculate the average value. That's how, we will get the output in a lower dimension. Now, this is only things are important for you to understand in this convolutional neural networks. You have image, then you have this feature maps. This feature maps basically are used, to in the convolution layer, to extract the important features. And now those feature maps will be passed to the pooling layer, and that data will be reduced to a lower dimension. Okay. And again, you can add one more convolution layer, which will again try to extract the data from the uh, data which we have in the pooling layer. And then again, the features will be extracted, and you might have you are seeing that, okay, every image will have different features, and every this filter maps which we are passing, okay. Now let's suppose in the convolutional layer, we are passing 10 different filter maps. So how many matrix you will get convoluted features? You will get 10 different convoluted features, because every filter map will produce a different convoluted features, right? And now here that's what is happening. Okay, here let's suppose I've used only 3 filter maps. And with these 3 filter maps, I'm able to I'm extracting only 3 different features, okay, from the data. That is the feature maps. But in this particular layer, I may use more number of filter maps. I may use 10 different filter maps. Now here my data will increase and I may get more feature maps. And then I will apply a pooling on each of these feature map to reduce the size. And now that data, I will go and pass it to the fully connected layer. Because ultimately what will happen is I will get the matrix as the output in every feature map. This is one matrix, this is one matrix, this is one matrix, right? Now these matrix will get flattened. Okay, it will be in the form of one single dimension. And that data will be considered as a separate column. So this would be a separate column, this would be a separate column, this would be a separate column. Now that data will be passed to the ANN. And now the ANN, you know how typically it works. Okay, it will go and find out again the hidden insights from the structured data and then process it to understand whether that particular data is related to boat or a house or a tree or that, and it will give the probability for each of these objects. And whichever object the probability is high, you can classify that particular object with that as that particular category. Okay, so this is as simple as that. Okay. Any questions, guys? So here there is no complex mathematics which is getting applied, but it is computationally it is very complex because you have to do it real time. Okay, and the real time processing such a big data is going to be complicated. But rest mathematics is simple. Okay, you're just taking a small binary matrix, square matrix, and then you are doing some multiplication on the original data, and then you are transforming that data into some other form. This is the primary thing what is happening in convolutional maps and the pooling layer. Any questions? All right. So here I will stop. Okay. So tomorrow either Vikrant will cover the use case or else we will first cover one more algorithm because he's also taking 7:30 to 8:30 batch. So we will check. Otherwise, I'll cover one more algorithm, which is long short-term memory, LSTM, okay, and recurrent neural networks. And once we understand these concepts, two use cases can Vikrant will take, or else I will, if he's not getting time, then I will take it. Okay, we'll cover the two use cases, okay, on CNN as well as on LSTM. LSTM, just to give you a high-level brief about it, this LSTM is a very, again, a next level kind of an algorithm. So firstly, to understand the LSTM, we need to understand the RNN. RNN is recurrent neural network. So the information will keep on getting transformed layer, layer by layer. And wherever there is a context, for example, you speak any sentence, every word in the has to be in the sequence, then only it makes sense. If I'm saying he's a good boy, okay. So first it has to start from he, then good, and then boy. If I say he, boy, good, it does not make sense, right? The context in the sequence is very important. So wherever the data, where the sequence is important, there we use this recurrent neural networks. So for example, time series data. If the sales 10 days back, the value of that particular sales was something, then the next day it got changed, the next day it got changed. By that time, 10 days before sales, till date, how was the pattern? It has to be in sequence, and only you will understand how the pattern is. You cannot just randomly pick the data like yesterday's data first and then today's data later. Something like that, if you randomly pick, it not make sense. So wherever there is a time series kind of a data, where the time is important, where the sequence is important, there we go with this uh, recurrent neural networks. So in the recurrent neural networks, one of the example I'll say intelligence. When you type something in Google search, you'll see that next word it predicts, right? It will say that okay, this could be the most probable word. Probably the user may type, when he's searching. So these kind of solutions can also be developed by these recurrent neural networks. But again, the recurrent neural networks has certain limitations. We will discuss more on those recurrent neural networks, and that limitation has been covered by these LSTM models, which is long short-term memory, and it is much more efficient and much more effective, and with low latency, you can process a lot of sequential data. So even the stock market prices, these LSTMs are predicting quite well, okay, which was not possible with the traditional time series algorithms. Okay, so we'll discuss about that particular algorithm tomorrow. All right, so here I'll stop. Anybody has any questions, feel free to ask, or else we'll connect tomorrow. Okay, so if there's no questions, then thanks, guys. We'll connect tomorrow. Thank you. Bye-bye.
Thank you, sir. Thank you.